All right, hello guys. Today we're going to talk about tensor parallelism. Wow, and I managed to say parallelism without twisting my tongue too much. So, um, let's get back to where we were before. We were playing with the models, with data parallelism, um, and we faced a challenge that with the 0, 1 to 3 data parallelism approaches, we can decrease the memory for gradients, for optimizer states, and for model parameters to a certain degree. But we can't do anything about activations. And also, at the same time, uh, we still have to manage to fit um, a single layer of the model on a single GPU. So there's that limitation as well. But we want to play with very long sequences and with very large models. Hence, welcome to tensor parallelism, and let's quickly remind ourselves what are tensors, what are matrices, and what we're trying to parallelize. So basically, all of the operations in our models, matrix, well, tensor multiplications, um, and in essence, it's input x multiplied by some weights w uh, that produces the output y. Um, and a quick recap of what it means to multiply a matrix is like we have a row, we take a column from w, we get a single value y. Another same row, another column, another value y. Another row, uh, another column, another column. So it's like row by column, and we get the y's. And we can notice that if we take the whole matrix X and multiply it by a single column W, we can get back a single row of Y, right? Like right here, first row, first column, it's Y11. Second row, first column, it's Y21. So basically, entire matrix X multiplied by the first column of W is our first column of Y, the output. And the second row of W, second column of Y. Wonderful. And that gets us the so-called column linear parallelization, where we broadcast the same matrix X, our input, to all of the GPUs that we have. We split our weights by columns. And then if we split our weights by columns, we get back different columns as results, and then we get do the altogether operation to kind of combine them, stack them on one another. And the authors of the book, they color coded everything, so we don't have to do it in our heads. Another way to parallelize matrix multiplication is to take a row. Well, yeah, kind of. Before I get to that, where we were before. First row, first column, y. And we can notice that it's basically the first element of x, x11, multiplied by 111, w11. It's a part of the output of y11, right? So we kind of sum what's highlighted in red with what's highlighted in orange and get our y. And that gets us to the next idea of how we can do parallelization. We can split W not by columns, but by rows this time. And we can take only the first column of X or only the second column of X. So like we split our input by columns, we split our W by rows. And when we do that, we get back the part of Y that we can sum up later. So once again, because we can, each number in Y is a sum of the multiplications that we did before. If we do this multiplications uh, for the entire column of X and for the entire row of W, we get back the whole Y, but we get back only part of this Y that we need to sum with the other part of Y, and we get back the original matrix. And that's called row linear parallelization. So basically, this time we split our input into columns or multiple columns. It depends on how many columns we have on the input. Um, we split our weights by rows. We get back as results partials of the final output, and then we combine the partials as a sum during the all reduce operation. And the final blueprint is that we combine both of these operations for column for all of our weights and most of our operations um, during the transformer, well, in the transformer block. And here, well, when we say most of the operations, we usually mean the attention mechanism and the subsequent MLP block. Um, and when I first saw this picture, I got very confused. I don't know about you guys, but did you get this picture like right from the start?
I guess there is somewhere implied ReLU, right?
Yeah, I think like implied ReLU is somewhere probably in the middle, but the ReLU is element wise, right? So it doesn't really matter. But what really puzzled me is that like why do we need to combine two operations really? Like what's the benefit? Why can't we do just like only column linear parallelism or only row linear parallelism and be done with it? So I tried to visualize it. So like why combine two operations? And we need to remind ourselves that usually when we have the MLP block after our detention mechanism, it's kind of it's fairly large. So it's usually uh, by the size of the 4H, if H is our embedding size. So it's fairly like we can call it fat. Um, and that means that when we kind of first do the first projection of our output from the attention block um, into the kind of internal layer of our MLP, we will get back the matrix of size h by 4h. And then when we project whatever we had there, we operate on the 4h layer, and then we will project back from the 4h to h. It's another matrix that we need to store of the size 4h by h. And then we finally get back our activations of the size b by h. But nevertheless, it means that in the middle of this process, uh, at some point, we have the matrix of the size h by 4h. Or actually b by 4h, right? Um, and when we split it column-wise, this is what happens. So we had b by h, and we multiply this b by h by only a single column of our h by 4h matrix, which kind of projects, kind of uh, distributes our weights in to our MLP block. And as a result, when we multiply b by h by a single column, we get a tiny vector b by 1. And we kind of, when we slice this h by 4h across multiple GPUs, we get multiple of these b by 1 blocks. And they're very small, right? And then when we do another multiplication, b by 1, we multiply by 1 by h, we get back our kind of partial of the final b by h block on each GPU. And the benefit here is that b by h is much, much smaller than, well, I say here that 4h by h, but really not 4h by h, b by 4h, right? So we don't care. H by 4h is the weights matrix, but the real activations that we would get if we multiply b by h by 4 by h by 4h would be b by 4h. So nevertheless, we get memory savings and activations uh, by the order of 4. And if we try to go, yeah, right here, if we try to go around it the other way, if we try to split it row-wise first, then yes, we can save some memory on the initial input, but then once we do the first multiplication, we instantly get b by 4h matrix on each GPU. And b by 4h is much, much bigger than b by h. And we also have to do all reduce separation in the middle before we can do the second multiplication. So well, it's a very bad deal, right? And that gets us to this blueprint where we broadcast our input onto all of the GPUs. We do column linear parallelism followed by the row linear parallelism. And the main benefit is that we don't need to materialize activations for this kind of fat region where we have these 4H. Mm, but well, where we should have gotten the 4H sized matrix. And well, it's not all rainbow and unicorns in this world. We still have to pay the price. So when we do this parallelization, we split the weights, we get the save on the weights, we get the save on activations, but at some point, actually right here in the all reduce block, we need to pay this price for the all reduce before we can do anything else with this, with our data. And we can't really overlap it with anything because we first need to collect the data, sum all these partials together before we can do anything useful with it. So this is like the idle block in our GPU. Um, and yeah. Now, well, regarding the attention mechanism, it's basically the same idea. So when we have multiple attention heads, uh, we get a non-square matrix. And if we split it column-wise, we can imagine that we calculate self-attention uh, only for a single head. So like if we have a very fat matrix with multiple attention heads, uh, each one of the GPUs can calculate, when we do column-wise parallelization, each one of the GPUs can calculate, we can imagine it as each one of the GPUs calculating attention for a single head. And then we kind of combine the output as the multi-attention result, multi-head attention result. Um, And as we can see, tensor parallelism, well, while it can substantially increase the max batch size, it's still nonlinear, right? So we increased our parallelism number of GPUs by 16 times, but the returns in the maximum batch size that we got is only what, 7, right? So it's nonlinear, and we have diminishing returns when we increase the number of GPUs. Um, at the same time, we can see that with the increasing tensor parallelism, we get smaller and smaller throughput. And that's to my best understanding because of this stuff. So the more GPUs we have, the more time we need to spend in this all reduce block where each one of the GPUs does nothing. On the bright side, with tensor parallelism equal to 8 or equal to 16, we can drastically reduce the memory for our model parameters, for gradients, right? They say gradients. but even for optimized states, and most importantly for, uh, well, in this picture, they show the same memory for activations, right? Which is a bit weird. And when I thought about it, I think it's because of the other operations that we can parallelize, and that's where the sequence parallelism comes in play. We still have layer norms which require us to collect activations from all of the GPUs to well basically produce layer norm. So I guess we don't see a decrease in memory, in activation memory, well, between tensor parallelism equal to 16 and tensor parallelism equal to 8, precisely because we still haven't parallelized all of the operations. And um, since sequence parallelism seems to be very complicated, I mean, I briefly glanced through it. I tried to dive deep. Um, And even the authors of the book say that they sometimes get confused with this stuff. They got us a table of what is sharded and what is not, and when it is sharded. Um, I think that today we'll wrap up with tensor parallelism and get back to sequence parallelism next time. And by next time, either me or somebody else who wants to do it will dive deeper into sequence parallelism, and we'll try to visualize each one of the operations as it happens to see what exactly happens with the memory step by step. But today, that's basically it. Any questions?
Um, I guess I'd like to understand maybe better the benefit of what is it, row-wise splitting.
Yeah, I think so.
Column-wise, I see, right? We kind of duplicate the input. We split out kind of the second
Yeah,
multiplicator column by column, and we get smaller outputs, which we then combine, kind of just glue together without summation, right? Just like
yeah.
concatenating.
So I think
But
that,
for row,
yeah, in my view, for rows here,
mhm,
like if we go back here for this would be row parallelism, right?
mhm, mhm.
So it seems like we don't get that much savings in memory because we still have to materialize this whole matrix, right? And
Yes.
in my view, to my best understanding, we need row parallelism here because we simply can't multiply this chunk b by 1 by the whole matrix for h by h. It's just not mathematically possible. So the only uh, how do we even multiply a b by 1 by 4h by h?
Let's see. So we take the input.
Yeah, so like say we got
Yeah,
here. We
this is
have
the output of the first multiplication.
yeah, we got it's the output of the first multiplication.
It's
If
sharded now.
if on each one of the GPUs we have this huge matrix, then
Mhm.
it does nothing because we can't multiply b by 1 by 4h
Mm.
by h. So
Yes. So it becomes an outer, what do you call it? Right? Outer product of these
yeah,
two vectors. Um,
so it
well,
kind of it doesn't
yeah.
make much sense once we have this
Yes.
guide. And
And we,
once we have it, so it only makes sense to kind of
Mhm.
multiply it by the first row, get the chunk, and then sum up all
Mhm.
of the chunks.
Correct. We don't want to do all reduce in between because that kind of kills the whole idea, because we never want to materialize this 4h by h thing in memory at any point.
Yeah, I mean, like if we do all reduce here, then
This is out of
uh,
necessity. Mhm.
yeah, if we do all reduce here, then like we can do all reduce here. Yes,
Yes.
but then we will have to on somewhere we would have to materialize this huge multiplication stuff.
Mhm. Makes sense. What if you did it the other way around? It's probably
Yeah, so
that doesn't make sense, right?
yeah,
Because
because of
or
this b by 4h.
yes. Okay. So I see. The row thing is just a necessity to do two multiplications in a row without materializing intermediate result.
Yeah, so the way I see it is that basically we need all of this stuff because our weight matrices, they are fat in a way. So we have this, like, they're not square. If they were square, probably it still would make some sense, right? I don't know if they were square, it still would make sense, I guess. I'm not sure.
Well, because of the second part, right? The second part doesn't need to be present on any GPU. Uh, Only like one row from it is needed.
Yeah, probably if they went, if it's not even about H or for each, maybe it's about the size of B. So if B was much greater than H, then we would have diminishing returns. And if B was much greater than H, it would make sense to probably do this, I guess.
Maybe, yeah, just like transpose both matrices and like
Oh, maybe yes.
switch them.
Maybe yes.
Hmm. Pretty cool.
Yeah, anything else? All right, I guess that's it. And see you next week for sequence parallelism, and I'll try to draw as many pretty pictures like this one as possible. All right, thank you guys. Have fun.
Okay. Bye.